In the next part of this lecture, we are going to talk about surface energy. So, what is surface energy? Well, surface energy is the energy that is related to any interfacial area. So, if you have an interface between two different faces, that interface will have a certain energy. And this is actually very easy to understand why this is the case. Let us have a look. Imagine I have a surface between two faces. I have a face A and a face B. And then I will see that if I have molecules in A, the A molecules here that are everywhere, there will be intermolecular forces between these molecules. So they will attract each other. And I will see that if I have a molecule that's down in phase A, it will be equally isotropically attracted by all its neighbors. But I have a molecule very close to the surface here. I will see that it is attracted to all its neighbors, but only the ones below. So there's no molecule A above it that attracts it. Yeah? Perhaps there are molecules in B. If it's, for example, if B is a solid or a liquid, there will be a lot of molecules that also attract A, but probably to a lesser extent than the A molecules attracting each other. So these are the cohesive forces. Or if B is a gas, then there will be very, very few, or even a vacuum, there will be very few molecules. So there will basically no molecules attracting. So I see that the molecule A here that is close to the surface will have a net attraction towards down, towards this bulk phase. And that means if I want to be molecule A at the surface, I have to have a certain energy to stay there, because naturally I'll be pulled back. So to get there, I need a certain energy. Another way to understand this intuitively is that imagine that I have two faces, A and B, or a phase interface, an interface to A, so for example to a vacuum, and imagine that there is no surface energy. What happens if I'm a molecule here, and there is no surface energy, then there is for me as a molecule no reason. Then, I mean, if there's no energy to be here, I can as well move to the left, to the right, down, or up, because there's no energy to keep me there. So that means that molecules at the interface will freely move into the other interface. And basically, this interface would kind of disappear, because nothing keeps the molecules there. So if I have a stable interface, I must have a surface energy there. An energy of a surface is called the surface energy, and it's expressed in joules per square meter, because it's per area kind of energy. So, can you, my first quiz question is the following. Can you think of an interface, for example a fluidic interface, that exhibits zero surface energy? So, and the question is, so yes or no, and if you can imagine such, could you give an example of such an interface? So, the answer is, can we imagine that? Yes, it is. It is possible to have an interface with zero energy, but it will not be a stable interface, as I explained. The interface will disappear. So an example of such an interface is when I fill a cup half with coffee, and then I pour carefully half of milk on top. Milk and coffee are intermixable, so the milk molecules, or the molecules in the milk phase, will move down, and when the coffee will go up, so I will get diffusive forces between the two, and this interface will disappear. But initially, when I just put a layer of coffee and a layer of milk on top of each other, I have an interface, but it has a zero energy. Another example is, for example, when I have two gases that are intermixable, and I have two spaces with gas and a wall in between. If I remove this wall, these two gases get in contact, and any fluid basically that's intermixable, it actually has a zero surface energy. Now, the next thing we're going to look at in surface energy is the fact that there is a unique relation between the curvature of an interface and the pressure drop over the interface. Yeah? And the best way to show this is with a soap film. So I have made a little green soap water here, and a little soap bubble. You see, I don't know if you can see that. I have a little soap bubble here in this holder. And the first thing I can see is that it's not very stable, but anyway, the first thing I can see is that this soap bubble, the surface of the soap bubble is flat. It's absolutely flat. And what is the pressure drop over the soap bubble? the pressure here is the same as the pressure here. So I have a zero pressure drop, gives me a flat surface. That's an observation. I'm going to try to blow a soap bubble. Let's see if this is stable enough to do. So I do like this. Yeah, it kind of worked. So what you saw is that if I blow in this direction, you see I put a pressure here. So the pressure at this side becomes larger than the pressure here. And what I see is that I create a surface that bulges out in this way. So I create a concave surface in this way. Huh? So I can see that in general rule is that the pressure on the concave side of a fluid interface is always higher than the pressure on the convex side of the fluid interface. And this is a rule that you can never forget if you think of how do I blow a soap bubble. Always think if I blow a soap bubble, I will see I have the hollow side towards me, the high pressure side has the hollow side, and the low pressure side is the rounded side, is the convex side. Huh? And this is a universal rule. So if I have zero pressure, it's flat. If I have a pressure drop, I create a hollow surface where the highest pressure is. So we go to the next quiz. And we can consider two types of in this quiz we consider two types of liquid interfaces. The first one is beer, and in beer you have CO2 bubbles. And now my question is, the pressure inside the bubble in the beer, is it larger than or smaller than the pressure in the surrounding liquid? The second example is dew droplets in air. You see dew droplets hanging on a spider web. They're small droplets, and the question is, the pressure inside these liquid droplets, is it larger than or smaller than the pressure of the surrounding air? So, what have I just explained? I have just explained that if I make a soap bubble and I blow, that the pressure on the hollow side is always larger than on the convex side. Yeah? So what do I see if I apply that here? I see that the bubble, the pressure inside the bubble must be larger than the liquid pressure, and in this case, the pressure inside the droplet is larger than the pressure inside the gas, than the air surrounding it. Yeah? So the pressure drop over the interface has nothing to do whether you have a gas or a liquid in the bubble. It has only to do with the shape. Okay? So in both cases, the pressure inside the small in the bubble and in the droplet is larger than in the surrounding fluid. And there is a formula that explains that, and that formula is called the Young-Laplace equation. And basically that says if I consider a curved surface that can look, for example, something like this. This is a section of a curved surface. I will be able to express a curvature by looking at a small part of that surface and then seeing I have this is a straight angle here. If I consider the curvature in the x direction and the curvature over this part here in the y direction, so let me take that in yellow, so the curvature over this side is now in red and here it's in black. So I can have a radius of curvature here, I can call that one Rx. And the radius of curvatures here I call Ry. Then the Young-Laplace equation says that the pressure drop, so again I know that underneath here, and this is underneath and this is a point above the surface, because it's concave here, the pressure here, P1 will be larger than P2, because it's a hollow, this is the hollow side. And I know that delta P, so the pressure drop over the system, equals the surface energy, that's the energy per square meter, times 1 over Rx plus 1 over Ry. This is a very simple formula that is universally true for a pressure drop over a phase interface that is curved. There's always a unique relation between the pressure drop and the curvature of an interface, of a stable interface. Okay? Well, let's look at this now in two examples. This is the next quiz. I'm going to consider two particular cases. The first case is where I have a perfectly circular hole. This is a circle in perspective, and I put a soap film in here, and I put a pressure from below, and I'm going to blow up a bubble surface that looks like this, with a radius r. What is the pressure drop over this r, over this interface? The second example is a similar system, but here, instead of making a circular opening, I'm going to make a groove in the surface. And I'm going to put pressure such that I get a cylindrical surface. So I get a cylindrical surface here. It looks like this. And again, we have a radius r here. What is the pressure drop over the cylindrical surface? So, the answer to that is, in the circular case, we look, of course, delta P equals gamma times 1 over Rx plus 1 over Ry. And in this case, Rx and Ry, it's a spherical surface, so Rx and Ry are the same and are equals to R. Both are R, so equals gamma times 1 over R plus 1 over R equals 2 gamma divided by R. Very simple formula. For a cylinder, I will see that delta P equals gamma times 1 over Rx plus 1 over Ry. Okay, what is Rx in this case? Well, I can say if this is the x direction, I can choose that, and I choose this to be the y direction. And I can see that in the x direction, Rx equals R. So equals gamma times 1 over R. And Ry, how much is Ry? Here, a point on the surface. And what is the radius of curvature in this direction? So I will see that if I consider this being part of a circle, it has to be a circle with an infinitely large radius. So Ry is infinitely large, so I get plus 1 over infinite. That's of course 0. And I get equals gamma over R. So I see the pressure drop over cylindrical surface with curvature radius R equals gamma over R over circular, it's 2 gamma over R. And you will find that any other solution, any other geometries that you can think of will have somewhere an in-between solution. And so if I have a free interface that is stable, I will know that that the pressure drop is constant, it's stationary, it's stable stationary. And so any system where the delta P is constant, where Rx plus Ry is constant, will give you a possible soap film kind of, or possible interface system that is in equilibrium. And there's a number of possibilities. This is basically geometry, but I had some, you can see there's also in the lecture notes, you see some different kind of soap films that you can have. Of course, the sphere is the easiest, that one you know. You can have cylinders, but you also can have things like catenoids, unduloids, and helicoids and nodoids, which are actually can be up to very complex shapes, but they are possible to make in soap bubbles and have a stationary shape.